I'm going to be computing the Cholesky factor in this video of matrix A, and I'm going to be doing it two different ways. Now, the Cholesky factor is a matrix R such that A equals R transpose times R. R will be upper triangular, and this is useful because we can use it to solve a system with A as the coefficient matrix using back substitution very simply and efficiently. So like I said, I'm going to be computing this two different ways. The first one will be the recursive method. And that gives us R transpose. This gives us R transpose. And we can do this because A is positive definite and it's symmetric as well. Positive definite means it has all positive eigenvalues, and symmetric means it's equal to its transpose, which we see is the case here. Okay, so let's do this. First, we're going to compute the first value, the first entry of the first row of our matrix R, and that's simply going to be the square root of the first entry of A. So we see that R11 equals square root of A11 equals square root of 16, which is 4. And then what we do is we take this bottom vector here and we denote that B transpose. Actually, I'm going to write it as the transpose, so we save space. B transpose is equal to 4, 8, 4. Then what we do is we take 1 over R, 1, 1, and we multiply it by B transpose to get S. S transpose is going to be equal to 1/4 B transpose, which is just going to be 1, 2, 1, like that. And then what we do is we need to compute a matrix called A wave, which is going to be an intermediary step. We're basically simplifying A down to smaller and smaller matrices until we get a 1-by-1 matrix and our algorithm is complete. So we see that A wave, A tilde if you prefer, 1 is going to be the 3-by-3 leading submatrix of matrix A, which in this case is going to be, or the 3-by-3 tail submatrix of matrix A. So this bit right here, that's going to be 10. I'll write that 0 a little closer there so it's a little less confusing. That's going to be 10, 8, 4, 8, 12, 10, 4, 10, 12, right there. And what we're going to do is we're going to take this S transpose, and we're going to multiply it by S. So we're going to be subtracting this from S transpose, which is, or actually we're going to take S first. S is going to be 1, 2, 1 like this. And we're going to be multiplying by the transpose of S, which is going to be 1, 2, 1 again, like this. All right. And when we compute that, we're going to get A wave 1 is going to be equal to 963, 688, 3811. All right. You can verify that if you want to. I'm not going to be going through the arithmetic steps here because that's going to take way too long. Okay, so this is our new matrix A wave. So we're going to be treating that just like we treated this matrix at the beginning, and we're going to be doing the same thing, except we're going to get S and B are going to have 2 entries, and it's going to get a little bit easier, a little less steps. So let's do that again. So we see that R22 will be the square root of the leading entry of A wave 1 equals the square root of A wave 1, 1, which is just the square root of 9, which is 3. Similarly, we take B transpose to be 6 and 3, this bit right here, right there, 6, 3. S transpose is just going to be 1 over 3 B transpose, which gives 2, 1. And just like before, then we would take A2 wave A2 wave to be the leading, or the what's it called? The tail submatrix, the 2 by 2 tail submatrix of matrix A wave 1, which is going to be this bit right here. That's going to give us 8, 8, 8, 11. And we're going to subtract that from S times S transpose, which is 2, 1, 2, 1, like that. And that's going to give us matrix A wave 2, which is going to be 4, 6, 6, 10. This is kind of an interesting property too, since we have that A was symmetric before and positive definite. All these like A waves, these submatrices we're finding, those are all also positive definite and symmetric. So that's an interesting little bit, and that's a good thing too, because otherwise this algorithm wouldn't work. You would take one iteration, A would maybe not be positive definite or not symmetric, and then you couldn't do this. But it's nice because it works here. Okay, so we have A2. So let's do the next thing. R33. R33 equals square root of 4 is 2. B transpose equals 6, the matrix 6. S transpose equals 1 over 2 times B transpose, which is 3, matrix 3. Okay, now we're on the last step here. We take A wave 3 to be the tail submatrix of wave A2, which is 10 here. Matrix, the 1 by 1 matrix with entry 10, minus 3 times 3, right? S transpose times S. They're 1 by 1, so that transpose is the same. And that gives us 1 here. The matrix 1, not the number 1. Almost done here. R44 equals the square root of 1, which is 1. And that's it. We're done. We're done. We have all the parts we need to get a matrix RT. Matrix RT, R transpose is going to be RT. And then what we're going to do here is we're going to put in all the pieces we just computed. So let's do that. Remember, our RT is going to be the lower triangular one, so we can put in the diagonal entries from the R values here. So we have 4, 3, 2, and 1 as the diagonal entries. 4, 3, 2, and 1. And remember, it's lower triangular, so we can just put zeros in the rest of this. All right. What about the bottom part of this matrix? Well, that's just going to be our S values. So the S value up here, right here, is 1, 2, 1. So that goes right here. 1, 2, 1. And then the next one is 2, 1, which is right here. 2, 1. And then S right here is 3. I'll get rid of that scratch right there that I accidentally wrote. Right there. Having trouble right now. All right, there we go. Okay, now this is our R transpose, which means that if we took the transpose of this, we would get A and multiplied it by this. So A would be, if we did 4, 0, 0, 0, 1, 3, 0, 0, 2, 2, 2, 0, 1, 1, 3, 1. It's kind of a crooked matrix. You get the picture. And if we multiply this by this matrix, the transpose, right here, That would be A. If you check that, it would work here. Okay, that was the recursive method of computing the Cholesky factor of A here. So let's do a different method. Let's do the bordered form method. And there's probably other methods too. I'm just going to be going over these two right now. So let's rewrite our matrix A in purple here so we know what we're doing. We have A equals 16, 4, 8, 4, 4, 10, 8, 4, 8, 8, 12, 10, 4, 4, 10, 12, like that. Okay, good. So like I said, we're going to be using the bordered form, so it's going to look like this. I can spell here. Bordered form. And this is going to give us R, by the way, the upper triangular version. The transpose, the transpose of R transpose. All right. So this kind of works backwards a little bit than what we just did. We're going to be starting with the smallest submatrix of A, and we're going to be working our way out to find R here. So for n equals 1, so 1 by 1 matrix, we have that A hat 1 equals the square root of 16. Or rather, A hat 1 is 16. That means R hat 1 is the square root of 16, which is 4. Matrix 4. So this A hat, that's just notation meaning the submatrix that contains 16. So the 1 by 1 principal leading submatrix there for matrix A. Okay, so we have our first part here. So now we're going to use that to compute the 2 by 2 version. And we're going to work all the way out until we have the 4 by 4 upper triangular matrix R here. So this is for n equals 1. Let's do n equals 2. So what we do is we take the principal leading submatrix that's 2 by 2 for A. So that's the matrix 16, 4, 4, 10. That gives us R2, which is going to be, we already computed the leading entry is going to be 4, so we know it's this one's going to be 4. We know it's upper triangular, so this is going to be 0. We don't know what these two values are though. These are going to be, we're going to call these x and y, and we're going to figure those out here. So we know that RT times R equals A. So if we took this is supposedly R. So what we can do is we can say, okay, RT times R equals A. So let's just write that in. So 4, 0, xy, that's RT, times 4, 0, xy right here. So this is RT, or R2 hat T, and this is R2 hat. That should give us A hat 2, if that makes sense. So that means that we know A hat 2 is 16, 4, 4, 10. So that means that x squared plus y squared equals 10, or also that 4 times x plus 0 times y is 4, right? Because when we multiply this row, we multiply these two rows together. We get 4 times x plus y times 4, and that we multiply that gives us this entry right here for matrix A hat. So we know that x has to be 1 then. X is 1. We know that we multiply these two entries right here, this one and this one, that's going to be this entry right here, 10. So we know that x squared plus y squared is 10. We know that x squared is 1. So that means y squared has to be 9. So that means y is 3. Y is 3. So that means our final matrix, r hat 2, is going to be 4, 0. Let's get rid of these here. 4, 0, 1, 3. All right. Good. Good, good, good. So let's do the next case. This is for n equals 3. Getting up in the complication here, but it's still not too bad. So we take the first leading 3 by 3 submatrix of A, which is the matrix 16, 4, 8, 4, 10, 8, 8, 8, 12. Let's write that down here. 16, 4, 8, 4, 10, 8, 8, 8, 12. Okay, so that means that R3, R hat 3, we already know the leading one is 4, right, from the first one. From n equals 2, we know that it's going to be 1, 0, 3 then, on this part. We know that R is upper triangular, so these values must be 0. We don't know this last column, though. We'll call this x, y, and z. All right, so let's do this then. So similarly, we know that RT equals R, or RT times R equals A. So we write the transpose like so. For 1x, 0, 3y, 0, 0, z times for 1x, 0, 3y, 0, 0, z. All right, so let's analyze this. We know that when we multiply this row times this column here, we're going to get this entry. So that means that x times 4 is 8, meaning x must be 2. All right, let's keep going here. That means when we multiply this row again right here times this column, we'll get x plus 3y equals 8. We know that x has to be 2, so so 2 plus 3y equals 8. 3y equals 6, y equals 2 as well. And finally, we know that when we multiply this row right here by this column, we're going to get this entry, 12. So we know that x squared plus y squared plus z squared is 12. So 4 plus 4 plus z squared is 12. So 8 plus z squared is 12, meaning z must be 2 also. Okay, so our final value for r hat 3 is going to be the matrix 4, 0, 0, 1, 3, 0, 2, 2, 2. All right, we're getting there. Last step. This is the 4 by 4 version here. This is the last thing we need to do. This is going to give us our final upper triangular matrix. All right, so let's do that here. N equals 4. So we take the first leading 4 by 4 principal submatrix of matrix A. Since matrix A is 4 by 4, we're just going to take matrix A then. So matrix A is 16, 4, 8, 4, 4, 10, 8, 4, 8, 8, 12, 10, 4, 4, 10, 12. Okay. All right. So let's do this here. So we know that R4 hat, which by the way, R4 hat is going to be our R value. This is the final one since R is going to be 4 by 4. That's going to be, the first part of it's going to be what we found up here. So 412, 032, 002, upper triangular, right? So these bottom ones are going to be zeros. Don't know these. W, X, Y, Z. Going to write it all out again. Take the transpose and multiply it by itself. So we'll get A, so we can solve for W, X, Y, and Z just like we were doing before. So that means we're going to have 412W, 032X, 002Y, 000Z times 412W, 032X, 002Y, 000Z. Okay. All right, so let's analyze this then. Multiply this row by this column. We'll get 16, right? Oh no, sorry, looking at the wrong thing. We'll get this entry right here, this 4. So W times 4 is 4. That means W is 1. Okay. Multiply the same row by this column. We'll get W plus 3X equals this entry, 4. So 1 plus 3X is 4. That means X must be 1 as well. Okay. All right. This row times this column. So 2W plus 2X plus 2Y. That'll give us this entry. So since W and X are 1, we have 2 plus 2 plus Y. 2 plus 2 plus Y is 10. Sorry, 2 plus 2 plus 2Y equals 10, right? Because there's a 2 there. So 2 plus 2 plus 2Y equals 10. That means 2Y equals 6. Y equals 3. And finally, multiply that row by this last column. W squared plus X squared plus Y squared plus Z squared is this entry, or 12. So that means let's do this. 1 plus 1 plus 9 plus Z squared is 12. 1 plus, Z is 1. Right. 1 squared plus 1 squared plus 3 squared plus Z squared equals 12. Z is 1. All right. Good. So let's write this again. Well, let's write it R this time since that's what it is. 4 0 0 0 1 3 0 0 2 2 2 0 1 1 3 1 for our Cholesky factor. And notice that that's the same exact thing that we got up here, right there, right? It's this version right here. That's R 4121 321. Just checking my own math here, making sure we got the same answer. Yep, we did. Both methods work. They have various uses, different ways. The recursive method's probably a little easier to program, but you know they both work. So I hope you found that useful.